Hi, thank you for the introduction. So this is joint work with Azadeh Farzan at the University of Toronto. And I'm going to talk about how can we synthesize a divide and conquer parallel implementation of a sequential program, which is in our case, our specification. I'm not going to argue why we need automatic parallelization, but is this going to be an automatic parallelization talk? Maybe not in the sense of compiler. So we are not going to provide safe code transformation, but rather a technique. And in our paradigm, we have a semantic treatment of functional equivalence. And we want to explore search spaces so that we can find a parallel implementation. So the main challenges in this talk is to define and explore efficiently these search spaces. And why divide and conquer? Because this is a parallel skeleton that can be used by programmers. So, for example, we have a tool that targets an implementation in TBB. So here, an example. I don't want you to read the whole code, but the main components are here, the body of a loop. So what is executed in each chunk, so the blocked range. And then we have a join, which recomputes the total result from partial results. For here, we join with the right-hand side, the sum right-hand side. So our input is a sequential program. We have a body B, and which updates a state S in a loop here. And we want to have an equivalent parallel implementation. So we simply split the loop, but then some problems arise. So we need to find this join operator, so the red one, and I'm going to refer to left and right threads to talk about this join operator. And we also probably need to find a new body and a new state in the loop so that we can actually parallelize the loop. So first problem, how can we find a join, and is it really difficult to find a join? So we have an example. This loop computes the second smallest example of an array S, and then we could think of a simple join, which takes simply the minimum of what the right thread has computed and the left thread has computed. But this is not the correct solution, and believe me, this is the correct solution, so a bit more complicated. And then, can we always find a join, whatever the loop we take as input? Of course, no. A simple example to illustrate that is the sortedness function. So it takes a sequence as input and say if it's sorted or not. So simply, here we have split the sequence in two, and the left array is sorted and the right array is sorted, but we have here two cases where the whole array is sorted, and in the second case, the whole array is not sorted. So in this case, we just need a prefix and a suffix of the input sequences of the different chunks to recompute the result in the join. But is passing prefixes of the input sequences enough? We have example where we need to actually add a really new computation in the loop. So, for example, the maximum tail sum, it computes the maximum sum of all the postfix sublists, so all the possible tails of a list. So here is the loop body to compute the maximum tail sum of the array A. And we just use one variable, MTS, and so we have just one assignment in the loop body. And now, let's imagine we have split the array in two, and we have the maximum tail sum of the left and the maximum tail sum of the right. But what can we do with the maximum tail sum of the left? There's information missing here, because the maximum tail sum of the left here is no more information about the whole tail of the array. So in this case, we would need the sum of the right array, so we can recompute the maximum tail sum of the whole example. And so this is the task of the programmer, to find this new computation. So the whole problem is, as I said, finding a join. And if there is no join, then can we find an extension of the loop so that we can parallelize this loop? And we provide a fully automated technique to solve these two problems. So on one hand, we construct a join for the divide and conquer problem. And if needed, we can lift the code so that the whole loop is parallelizable. And we implemented it in a tool, so you can find it on GitHub. So how do we synthesize this join? We use syntax-guided synthesis, so two main components, correctness specification and syntactic restrictions. So the correctness specification is actually the statement of our problem. On one side, we have this sequential computation, so the B function takes the whole sequence as input, and we have at the end a state S. And we are trying to find this red dot so that joining the two computations gives us the same state at the end. In this problem, the specification is independent from the problem instance. We just have to replace the function name in the correctness specification. But the main challenge is to find the good syntactic restrictions. So the syntactic restrictions will define the search space for the join. So this is our unknown here. So we have to make it small so the problem is tractable and scalable. And it has to include the solution, so we actually find the solution. Our idea was to build the sketch from the code of the sequential function. So to do that, we simply, for example, in the second smallest example, we take the sequential function. We replace every occurrence of a variable by a hole, so we have the red, green, and blue hole. And then the solver will fill these holes with an expression grammar so that in the end, the expression of the join will satisfy the correctness specification. So in this case, we use a simple grammar, and the red hole is filled by a complete expression, and the green and blue, in the green and blue case, we just need one value. So again, with the left and right thread, the left and right threads results. And we have theoretical guarantees that this syntactic restriction, by just simply building a sketch, partial program from the sequential implementation, is enough, and is also good enough so we do not miss any syntactic restrictions. And these reasonable assumptions are intuitively, it's just we can build a summary of the function we are trying to parallelize that has a limited length. So for example, if you want to build a summary of the sum function, you just need to build an array with the sum of the whole array in one cell. And then our second problem, what if the loop is not parallelizable? So we try to find a join does not exist, and we try to find an extension of the loop or a new computation so that this new loop, that is just an extension of the old one, is parallelizable. So we have the sequential computation starting from the initial state f of empty list, and we read the inputs S0, S1 until the last input, and we have a final state. And we split this computation. So in the sequential setting, the right thread should start with the last state of the left thread. But in the parallel setting, we don't actually have access to this state. So we try to see how in the right thread the computation goes, assuming that we have this initial state. So we unfold for the first read. We read the first input and we look at the expression, unfold the second time, and then this state that we didn't have access to is actually goes deeper in the expression. And then we try to transform the expression, so we separate the different parts of the computation in this expression. So we have, on one hand, this what the left thread was computing, so the red state here. On the other hand, we're trying to isolate what the right thread would be computing if it were in the parallel setting, so starting from the initial state f of empty list. And we might have this green expression, which is something, if we stop the computation here, we have what the right thread was computing in the purple. We have what the left thread was computing in green, but we don't have this green expression. So we are trying then, by continuing to unfold, to find a computation that will summarize this information in green. So we iterate until we reach a fixed point, and we have found this f auxiliary, which take as input the current input, and the auxiliary variable, which is, so we had the expression depending on the input k plus 2 and k plus 1 in this case, and then a function of this expression and the new input on k plus 3. So the algorithm will iterate until it has found such a function, or iterate if it doesn't find this function and there is still a green expression, it can continue to iterate and fail. I will illustrate this with our maximum tail sum example. So the first unfolding, we started from the red state, so here in MTS0, and we read the input A1. Then second unfolding, I'm reading the input A2, and so the red state goes deeper in the expression, and cost is the number of operators I have above the red state. Our idea was that by reducing the cost of this expression, so the depth of the red state, we can find an expression where, so here I'm distributing plus over max, and then using associativity of max to have this expression, and now we have a cost equal to 2, and this expression, which is this add the input A2 to the previous A1. And third unfolding, after all these steps of reducing the cost of the expression, we find that we can use again this function, this summing function, to find this variable. So we have found a new auxiliary, which is the sum of the elements of the array. So here the critical component is the normalization procedure. Can we have these rules, and so can we have a procedure that will transform our initial expression where the state was deep in the expression and it was hard to separate what the right thread and the left thread was computing, to an expression where all these expressions are split. And so we need a set of algebraic rules to transform the expressions. So, for example, distributivity, and a cost function that will define the strategy. So we are searching using the algebraic rule, and using the cost function that reduces the number and the depth of the occurrences of state variables in the expression. We try to go to this final expression we want to reach. We also have theoretical guarantees for this algorithm. So assuming we have this ideal normalization procedure that splits the expression into what the left thread was computing, what the right thread was computing, and this auxiliary, then we know that if the algorithm terminates with or without new auxiliary, then the function is parallelizable. And also, if a constant extension, such as the sum, exists, then we can find this extension. So, what about correctness? The problem with the syntax-guided synthesis is that we cannot express our correctness over inputs of unbounded size. And so, in the end, the solution we have is we know that it is correct on inputs of bounded size only. And our solution was to automatically, once we have the solution, generate a proof in the Daphne program verifier when possible, and then prove that the equivalence between the sequential implementation and this new divide and conquer implementation. So here are some of the examples we treated. So the largest synthesis time is for examples that use nonlinear operators such as polynomial, so over 100 seconds, but it's still acceptable, and we can synthesize solutions in acceptable time. So from 1 second for the sum to the polynomial, or A to Y example in over 100 of seconds. And then here we have in green examples that just depend on prefix and suffix inputs from the input sequences. And in orange, we had to find a whole new computation, so by using this more deductive synthesis approach to find the auxiliary computation. We also evaluated the efficacy of the synthesized code. So using the TBB implementation we generate automatically, we had on all the cases linear speedup up to 32 cores, but then we know that TBB has some problems with when we have more than 32 cores. So that's why the Hamming example has a weird speed up after 32 cores. So, in conclusion, so we found that we have found a technique that scales to different types of divide and conquer settings. So from this function that didn't need any auxiliary to this prefix and suffix that are actually just a sub-problem of finding this general accumulator. And we are exploring other forms of divide. So in this case, we just split the sequence. So it's just a concatenation over sequences. We would like to extend the technique to non-scalar state variables, so arrays. And we also want to explore what we can do with multiple nested loops. So, thank you for listening.
Thank you very much. We have about 5 minutes for questions.
Similar set of example can be parallelized by using matrix multiplication, as you know. So, is there any example to which matrix multiplication-based formalization is inapplicable, but yours is applicable?
I'm sorry.
Yeah. In a paper, you cite some paper based on parallelization based on matrix multiplication. Mm-hmm. That formalization and approach is applicable to similar set of examples. So example loops. So what is the difference between yours and then existing one in expressiveness or applicability?
I'm not sure to understand exactly what you mean, but so our technique is only on the applicable on function from sequences to scalars. So this is we don't tackle the problem of multiple nested loops or.
Oh, okay. I think it is better to discuss later. Okay. And answer. What? Okay. I have another question. Can you deal with some scan? So some prefix sounds. So not only reduction. How about scan-like loop?
We didn't try to.
Okay.
Please go back to slide 12.
Slide
Slide 12.
12.
Page 12. Yeah, I'd like to see the hidden part in the right answer. The tree is monadic tree like this?
Yes.
Or, okay, that's the question. So if we consider the balanced binary tree computation for this, then maybe something should be changed in the formalization.
Tree computation. Yes. No, it's not necessarily balanced because because of the we can express the problem as the problem to find if this function is a homomorphism. So, and the join here is associative, so we can reorganize the tree as we want. So the join we will find.
Yeah. So if the tree is really the monadic tree,
yes,
then we can use non-associative operator.
We can use associativity.
But
so
in
that it's
this work, you use associative operators, so you can use any kind of tree.
Yes.
Okay.
Very nice work. Can you go to slide 26, back where you were? So all the rows where you have auxiliaries, these were done through the algebraic unfolding method, right?
Yes.
And did you try to use the syntax-guided technique to invent the auxiliary?
Yes, we thought about it, but since we have to do it at every unfolding, and in this case, it's often like we found that just we don't need a big set of reduction rules. It's faster to use this, and the syntax-guided synthesis technique will not scale because of the several unfoldings and then the complexity at the end of the full expression.
You could probably do it without unfolding, right? Just essentially the way you complete your initial skeleton, you could also invent another auxiliary expression.
Yes, but then we could just give the problem to the syntax-guided solver and say, find me a new expression. But we think that we didn't think of any way to specialize to find a more narrow sketch in this case.
Mm-hmm. Okay, thank you.
All right, any other questions will have to be taken offline. Let's thank Victor again.